when we are talking about energy efficiency, remember that to improve the energy efficiency, we are analyzing a building and we want to improve the energy efficiency of this building. What have we done? First, increase thermal insulation. So that's the best thing we can do, but the best. If we have enough thermal insulation, we know that we will increase energy efficiency. It's not an option. Oh, should I put more thermal insulation? The more thermal insulation, the better the energy efficiency. What's the downside of this? That we can have walls with 2 or 3 feet. I mean the thickness, because it's impossible, and we have to. We need the room area to be the right room area, so we cannot reduce the area of the building by increasing the thermal the thickness of the wall. So there's a compromise. And what's that? Okay, so from now on, we are going to work with the passive house standards. So we are going to increase thermal insulation until we get passive house standards. So what are these passive house standards? Passive house, as I told you, it's a concept that I think it was developed in Germany. In Germany, the weather is terrible. It's so cold, it's raining, it's snowing. And they developed this idea because they understood that they were spending a lot of energy on heating up buildings. A lot of energy, probably 40% of the energy that country consumed was about heating up the buildings. So, okay, increase the thermal insulation, reduce the energy consumption of the building, and then we can spend that energy on other things that are more productive. Okay, so that's the concept of this passive house. So what are the passive house standards? If you Google on the internet the R value, look at this. Deep insulated walls, most buildings require envelope performance levels in the range of R40 to R60 for walls, R50 to R90 for roofs, and R30 to R50 for slab assemblies. This is either the floor or the pavement walls. Okay, so what is the number that we have to remember? 50. Okay, so we have this number. We don't, okay, for walls, it was something, for roof, something different. R50, it's a good number for everything. So what does it mean, R50? If we have our Excel file, if you are analyzing your walls, in this case, in this analysis, the R value is 25. How can we make this value R50? Just by increasing the thermal insulation. Here we have thermal insulation, 6 inches, we have 25. If we have 10 inches, this is 40. We need probably 12 inches, and this is 47, we're getting there. 14 inches, it's 54. So probably with 13, we have 51. Okay, so that's it. There is no secret to this requirement. We have to increase the thermal insulation. And increasing the thermal insulation means that we have 13 inches of thermal insulation. 13 inches is more than 1 foot, and that's only the thermal insulation. Then we need the brick, whatever. Look at the thickness of this wall. We have 4 inches of brick, 2 inches of air cavity, 13 inches of thermal insulation, and 5. So we end up having 20 inches. 20 inches, almost 2 feet. Okay, so if we are committed to these passive house standards, high efficiency buildings, the R value it's greater than 50, and that means around 20-inch walls, roofs. So that's it. Okay, so this is what we are dealing with. If you want to save some space, we can, if we want to get the same thermal insulation with less thickness, we can change the thermal insulating material. If we use polystyrene, extruded polystyrene, with 13 inches, we have 112. So that means that we can reduce this probably to 8 inches. With 8, we have 70. Even with 6, we have 54. So that's interesting. If we want to reduce the thickness, we reduce the thickness of the wall a lot, and we still have this R value above 50. But we have to use extruded polystyrene. If we use extruded polystyrene, probably it's the most efficient thermal insulating material. The problem is the carbon footprint of this extruded polystyrene higher than any other materials. Can we do something in the middle? Can we use fiberglass, for example? If we use fiberglass, 6 inches is not enough, but probably 10. Okay, so with 10, we are getting there. With 11, we are above 50. So what can we do? First, if we are designing passive house buildings, this value has to be close to 50. If well, depending on the thermal insulating material that we are using, we have a thicker or a thinner wall. But now with this tool, you can test different options. Okay, so what if I use fiberglass? What if I use this? What if I use cellulose? Probably cellulose is the best material in terms of carbon footprint because it's made of wood. It's smashed wood. It's a natural material, so we don't have to spend a lot of energy manufacturing this material. But with cellulose, 11 inches, it's far from being enough, and probably we will need 20 inches. 20 inches, we are still far from that goal. Okay, so it depends. But now you have options, and you can understand the goal is 50. And then that's the tool that we have to, or this is the layer, because by changing the brick, we can increase to double the thickness of the brick, and that goes from 37 to 38. So it's pointless. Okay, we can increase the gypsum wall 2 inches, and we go from 37 to 39. So that's not an option. The only option that makes a difference, it's increasing the thickness of the thermal insulating material or changing the thermal insulating material. Okay, so this is the first thing we have to do. We have to increase thermal insulation. Passive house standards are mandatory in Massachusetts, and it won't be long until they are mandatory in all this Northeast region in the United States, because it's a very effective measure, and everybody understands that we have to increase the thermal insulation. So it's not like, yeah, but if we do this, but then we have, it's very straightforward. What is something that goes well with passive house standards? The R value has to be around 50. And that means that we have very thick walls. We have 1 foot, from 1 to 2 feet is the thickness of this kind of walls to meet the passive house standards. So in your design, you don't have to analyze it before and after. You are designing something from scratch, and the goal or the target is R50. So your walls are going to be from 1 foot to 2 feet thick. Keep that in mind. So I don't want to see walls that are 5 inches. Doesn't make sense, because we need to achieve this target of R50. So first, we have to increase thermal insulation. What other options we have to increase the energy efficiency? We have to use a heat recovery. Especially both in residential and commercial buildings. Okay, so if we use a heat recovery in both residential and commercial buildings, we can save a lot of energy. You see that probably the most efficient measure was to place a heat recovery in your building. So it was the measure that achieved the greatest savings. So again, it's not an option. So we have to use a heat recovery. In commercial buildings, it's something that it's mandatory. You can't design a commercial building without this kind of heat recovery. For residential building, it's an option. But again, if we want to meet the passive house standards, probably we need to use heat recoveries. Heat recovery is not something that affects the design a lot, but well, you have to keep in mind it's a device and probably we will need that. So we need it. And what's the third measure of energy efficiency? It's the solar heat gains. Solar heat gains, we need to maximize solar heat gains in winter and minimize solar heat gains in summer. Again, everybody understands that in winter, if we open windows to the south orientation, we can make the most of the sun. We can gain a lot of energy. In summer, if we do the same thing, we gain a lot of energy and we have to get rid of it. So that's the theory. How can we do that? First, orientation of the windows. In this area of the world, in cold countries, south is better. South. Then we have another tool, which is the solar heat gain coefficient. Solar heat gain coefficient. That's the amount of solar energy that enters the building. In theory, we need a high solar heat gain coefficient in winter and a very low solar heat gain coefficient in summer. Well, unfortunately, we can't do that. We can't change the solar heat gain coefficient from summer to winter. So we need to understand where we are. In this area of the world, I would say that a high solar heat gain coefficient would be beneficial, especially if we are using the building mostly in winter. Okay, so that's we have to understand what happens. So that's why we have the tool and we can change the solar heat gain coefficient of the windows in that tool, in that Excel file, and we can analyze if it's good or bad from this point of view. Okay, but that's another concept that we need to understand. We have the orientation of the window and the solar heat gain coefficient. And finally, we need shading devices. In shading devices, we have an overhang, we have louvers, we have blinds, so on, so forth. Okay. And that affects the design. The solar heat gain coefficient doesn't affect the design because it's a film that or a coating that we apply to the glass, and it doesn't change the aspect of the building. The shading devices, they change the design of the building, and it can change the design of the building for better. For example, if we open okay, so those are louvers. Louvers are elements like this that we have light, but we don't have direct sun. We can have horizontal louvers, vertical louvers, and we can, I think it's it's something that can make the building better, designing this kind of shading devices, especially when we have a curtain wall, we have a lot of area of glass. Having these kind of elements can help reduce that energy, especially in summer. And we can have interesting design ideas by using these elements. Okay, especially when they are movable. When they are movable elements, we can allow sun entering the building in winter, sorry, and we can block the sun in summer. So having this kind of elements, it's always an interesting, and when it comes to design, you can make the most of it. Okay, so it can be part of the design of your facade using these kind of elements to protect windows. And we can do that. We can close them to block the sun, or we can open them to allow sun to enter the building. Okay, so there are a lot of examples, and this is a very efficient measure especially to save energy in summer, just blocking the sun. So that's it. Okay, so when we are using energy efficiency, we don't have to think about, oh, no, that's it. Finally, we need renewable energy. And with renewable energy, we mean solar panels. But don't be naive. Don't think, okay, I can have that design, then I will install a lot of solar panels on my building, and it will be sustainable. No, you have to do all this first, and finally, we have to install the minimum amount of solar panels or renewable energy devices, because we have increased the energy efficiency of the building with all these measures. So it's quite easy. Increase the thermal insulation, use heat recoveries, solar heat gains. We need to understand this, and we need the solar analysis of the building. So the first thing we have to do is a solar of the building and the site. Okay, so we need to analyze the site in terms of the sun. And then the idea, we have to maximize solar heat gains in winter, we have to minimize solar heat gains in summer, and we have to play with the orientation of the windows, the solar heat gain coefficient, and shading devices. That's it. And finally, once we have done all this, we can use renewable energy solar panels in buildings. So when as of next week, if we meet here, if you show me your design, I need to see thick walls because we need thermal insulation. Heat recovery, it's something that we don't have to see in the projects, but the solar analysis, yes. So if you don't have windows, start thinking about the windows or the openings, where you need the openings, what kind of openings. Do you have louvers? Do we have shading devices? How can we do, and how that will affect your design? And then renewable energy. If we need solar panels, look at this building. This building has this PV array, and of course affects the design. So you can, if you remove that PV array from this building, this building will look like something completely different. Okay, so maybe it's better or maybe it's worse, but you need to keep that in mind if you want to implement renewable energy in your buildings. It has an impact on the building design. Okay, so this is what we are going to do. In this assignment, we are not going to analyze the first option, a second option. No, we have to do this because we know that it will be good. Okay. And we are going to use the PV watts tool. PV watts, where as far as I know, your building is in Keene, New Hampshire. It's on campus. Okay, so we're going to use data from Keene. What we are doing, we have to do it again if we change the place. Okay, so we are going to deal with 24 hours times 365 65 days in Keene, New Hampshire. If you were designing a building in any other place, you would have to do the same thing. You will have to download this data from that location. So we are going to work with Keene, New Hampshire. We are going to use this tool for the last part. When we talk about renewable energy, we will use PV watts again to assess the amount of energy that we can produce with our panels. Today, we're going just to download the parameters. We're not even working with the tilt and the azimuth. We're not even doing that. Okay, so we go to results and we are going to download hourly, because today we're going to deal only with the outdoor temperature, throughout the year. So just get to this point, download the hourly Excel file, and open the PV watts. There you go. Okay, so here we have month, day, hour. We are not even going to use the beam irradiance in the ambient temperature. We're not going to use that. We're going to use only the temperature. That's the only column that we're going to use today. So I'm going to delete all this. And I don't want to use the wind speed, the cell temperature. I don't want that. I don't want even the beam irradiance. We will use it to analyze the performance of the windows, not today. So we just want the ambient temperature, by default, we have Celsius. So what I need now is outdoor temperature in Fahrenheit. That's the only thing we are going to use today. So we have the outdoor temperature in Fahrenheit. So what's the outdoor temperature? What's the conversion between Celsius to Fahrenheit? Celsius to Fahrenheit. So it's 9 divided by 5 times the Celsius plus 32. So let's do it. So this equals the Celsius temperature times 9 divided by 5. I'm going to use a parenthesis here. This is plus 32. Click OK. And -2 Celsius is 24.8 Fahrenheit. If I want to, because now I want to drag this cell or this formula all the way down. We have, until the end of this, we have 8,762 and 60 cells. So we can drag it down, or we can double click here. No, we can't. Okay, so let's drag it down, all the way down. There you go. Okay, so we have the temperature in Fahrenheit throughout the year. And now I want to open a new tab or a new sheet on this file, and I want to copy these results. Okay, so I'm going to select all this, Control C, Control V. And now I have the month, day, hour. Do I need the ambient temperature in Celsius? I can delete that cell. If I delete that cell, you see that there's a problem here because this number is related to the other one. Okay, so I'm not going to delete it, but I can hide it. Because all I need is the outdoor temperature in Fahrenheit. Okay, so now I want the thermal loads. I have calculated thermal loads just when I was working with walls and windows, and I'm going to name that one yearly values. I have calculated this, the ventilation loads, the walls thermal loads, the roof thermal loads, the window thermal loads, just for one value, for a value of indoor minus outdoor temperature. Okay, so I have this, and I have calculated this times indoor minus outdoor temperature. Like this. But now I want this value every single hour of the year. So that's why there's a lot of data there, 8,760, whatever, and we have to do that now. So I'm going to calculate the walls with the north orientation. I want to calculate the walls with the south orientation. The east and the west. Okay. Then what else? I have the roofs, the basement, and windows. Okay, so I'm going to calculate thermal loads hourly, every single hour for all these elements that I have analyzed before. And we need ventilation too. And how can we do it? Well, the formula, it's going to be it's always the same. We have the formula of thermal loads. It's the U value times the area times indoor minus outdoor temperature. We have calculated the UA. UA is U value times the area, and then we have to multiply times indoor minus outdoor temperature. What's the only thing that changes? The outdoor temperature. Now the U value is fixed. We don't change the U value of the wall. The area of the wall, we don't change it. Indoor temperature, we can consider that it's always constant around comfort, 70 Fahrenheit or 72 or 68 or something like that. And the outdoor temperature now changes because we have a different outdoor temperature every single hour. Okay, so in winter, we have low temperatures. We have even negative Fahrenheit. And in summer, there will be temperatures close to 70, 60, sometimes 80. Okay. So those are the temperatures in summer. But I'm going to add something else, something very useful. So I'm going to insert a new column here. And this is the schedule. So what's the schedule? It's the amount of hours that the building is open every day. So how can we do that? Well, I'm going to consider that 0 means that the building is closed, that nobody's there, and 1 means that the building is open. So then on every single day, this is the first day, we have from hour 0 to hour 23. So that's the first day. What's the schedule? If I consider that the building opens at 7 a.m., so I can have 0 up to 7 a.m. So at 7 a.m. we have 1, and it's open until 8 p.m. So I have 1. And at 9 p.m., the building is closed again. 0, 0, 0. Okay, so why am I doing this? Because I'm consuming energy only when the building is open. If the building is closed, I don't consume any energy. So I can't multiply times 24 hours. And if I have a building open 24 hours, all these values will be 1. Okay, but in commercial buildings, the building isn't open 24 hours. Well, maybe there are some cases in which buildings are open 24 hours. Usually they are not. Okay, so we have a schedule, and this can be the schedule. So the building is open from 7 a.m. up to 8 p.m. Maybe the building has a couple of hours here for lunch. It's closed again. I don't know. Anyway, here you can select the schedule. The thing is that we have to copy that schedule every single day of the year. So how can we do it? It's easy, but it's a little time consuming. So I can copy all these cells and I can paste them here. Right. I copy all these 24 cells, Control Z, and then Control V. I copy this and I keep copying, Control V. Do I have to do this 365 times? Well, I can do that, or when I have copied some of them, I can Control C and I can paste. So it's a little faster. And once I'm done with a lot of cells, I can copy all of them, Control C, and then I can paste a lot of cells at once. Control V, we're getting there. Okay, so I can delete all those. It's time consuming, but it's 30 seconds, so it's not that much. Now I have the schedule every single day. Okay, so every day I open the building at at 7 p.m. a.m. and the building is closed at 8, well, at 9 p.m. Okay, what's the formula of the hourly energy consumption of northern walls? Well, I have to go to the walls tab, because this formula is going to be always UA, U value times the area, times indoor minus outdoor temperature. So all these, the first three figures, I can find these three figures in the walls tab, but the outdoor temperature, it's not in walls, it's in these yearly values or yearly outdoor temperature. So how can we do that? That equals, and then I want to change the tab. Now I'm in walls, and if we are dealing with northern walls, this is the walls in the north, that's the UA value, the U value, the thermal transmittance, times the area. So I have this. So this is the U value times. What's the indoor temperature? The indoor temperature is the temperature that I have declared here, indoor temperature. And now minus, what's the outdoor temperature? The outdoor temperature is the temperature that I have in this tab. This is the temperature. And then parentheses. So you see that here we have walls, because we are in this heat walls. The cell is I77. Walls T5 is the indoor temperature. Yearly, it's this heat. And here now, it's this yearly F2 is the outdoor temperature. So we can click OK. And this is the energy consumption on January the 1st, but the building is closed. Okay, so I'm going to multiply this times the schedule cell, and now it's 0. Okay, so I don't have any energy consumption, because at that time, on January the 1st at midnight, the building is closed. Most likely it will happen with most of the buildings. Okay, what if I drag it down? If I drag it down, I have this issue. Why? Because I have to deal with the dollars. This cell is fixed, so I have to go to dollar I, dollar 77, and the indoor temperature is fixed. So I have to type $D, $5. Then the rest of the figures, they don't need a dollar, because as we drag it, we will have this. Okay, so let's drag it now, and let's analyze the first day. So I have to go to January the 1st, hour 23. That makes sense, because I have 0 when we don't have any. Yeah, when the schedule is 0, the building is closed. When the building is open, I have energy consumption. This number, it's weird, so I'm going to format the cell, and I don't want any decimal places, because the values are dollars. Why? Symbol, none. Okay, and now I go to the format painter, and I click this, and I don't have any decimal places. What can I do now? I have to keep going up to the. Okay, so now it works. The first time didn't work, but look at this. Now we don't have to drag it anymore. Once we have dragged the first column all the way down, Excel understands that, probably this guy wants to copy this formula up to the last value. So if you select this element and you double click here, you will see that now we have energy consumption from day 1 until day 365. Okay. Wow, a lot of yeah.
Where did you get the schedule from? Sorry.
Where did I get the schedule?
Yeah.
I made it up.
Oh.
I mean, it's something that most of the commercial buildings, they open at 7 a.m. and they close at 9 p.m. So that's what I did, but it's not a single family house, probably single family houses, you don't have a schedule, so it's the system is operating 24 hours a day. On campus, I know, I think most of the buildings open at 7 or 8. Well, classes here, the building is open, but it doesn't mean that the building is open if it's empty. We don't have the heating system on. And we noticed today that it's cold in this classroom. And why is it? Because probably the system started operating at 8 a.m. Or 7:30 or whatever. So it didn't have time to warm up the we are working at a wonderful temperature of 66 Fahrenheit, which is slightly cold. Anyway, in a couple of, well, in 1 hour or 2 hours, the temperature will be, but that's the effect of time. And this is something that we don't have in this tool. Okay, so the effect of time, how much time it gets to get to comfort temperature. If the building has been locked for over the weekend, we didn't have any any heating system in the building. It's not enough turning on the system at 8 a.m. It takes time. How much time? It depends on the thermal mass of the building. It depends on a lot of things, but the effect of time matters. And this is something that we can't have in this because the physics is quite complicated. But anyway, we have a good approach here. So this is the walls north. What about the walls south? For the walls south, we have to go to the wall again. Well, first, I have to type equals. What's the first? I have to go to the southern walls, UA times indoor temperature minus outdoor temperature. So I have to go to that file, and the outdoor temperature is this one. Close parentheses, and remember that I need here dollar vaya. Do it again. Walls UA times parentheses indoor temperature minus outdoor temperature parentheses, and now I need to type dollar. It's $I, $17, $D, $5 times the schedule. Okay, so the first hour is 0. I double click. Whoop, everything's there. Same thing with east. Equals. I have to go to walls again. East. This is the UA times indoor temperature minus outdoor temperature, dollars, and dollar times schedule. Double click, hop, and west, that equals, go back to the walls, UA times, parentheses, indoor temperature minus yearly outdoor temperature, dollars, dollar, times schedule. And double click. Well, okay, so in a reasonable amount of time, we have a lot of information. We have hourly energy consumptions. The problem is that here we have a lot of decimals. So I have to format all this. Probably I'm going, before doing anything else, I'm going to select all the cells. And I'm going to use the format. And I'm going to select number and no decimal places. Okay, so now I do everything at once. Okay, so now I can do the same thing with the roofs. If I do the same with the roofs, I'm going to do it just with the roofs, and then you will have to do it with the basement, windows, and ventilation, and all that stuff. But let's do it with the roofs. So the roof is equals. I go to the roof tab. Here we have the UA. It's the U average times the area of the roof. So that's the value times indoor temperature minus, I go to the yearly, and this is the outdoor temperature. Don't forget the dollars. And times the schedule. Double click. There you go. Okay, so we can do the same with the basement, we can do the same with the windows, and we can do the same with the ventilation loads, because everything is affected by the outdoor temperature and it's affected by the schedule. So for the, but now, what do we need? We need to understand the monthly consumption of the monthly energy consumption that we need because we have walls, because we have roofs, because we have a basement, and we have a window. So how can we do that? And in addition, we have heating and we have cooling. Look at this. So what's the energy consumption? In January, all these numbers are positive. Okay, so all the numbers are positive. But if we go farther, look at this. This is August the 17th. We have negative numbers, and suddenly we have positive numbers. Why is that? When is the number negative? When the outdoor temperature is higher than the indoor temperature, we have a negative number, because the formula, it's always the same. The formula is always indoor minus outdoor temperature. So what does it mean? Positive numbers means heating, negative numbers means cooling. Okay. Positive numbers heating and negative numbers cooling. But there are days in which we need heating, we need cooling, but as of this point, I will need heating. Why is that? Well, maybe the temperature is high enough at noon or close to noon, and then in the evening, the temperature drops. So that the same day I might need cooling, but then the last hours of the day I might need heating. Okay, so that introduces something more complicated to this analysis. It's not just, oh, in winter I need heating, in summer I need cooling. No, it's not that simple. There might some days in summer I might need heating, and if we introduce the solar heat gains, some days in winter we might need cooling. We haven't introduced the solar heat gains yet. Okay, so that's this Excel file is going to become more and more complicated as we work with it. So far, we are just analyzing the thermal loads to the walls and to the roofs. But even the thermal loads through the walls and through the roofs, it's not that simple that summer cooling, winter heating, because there are days in May, some days in May we will need heating the whole day. Some days in May we will need cooling the whole day. Or some days in May we will need heating at the beginning of the day, and then we will need cooling at the end of the day. So things can be complicated. Anyway, we're going to do that. We want to analyze this on a monthly basis, but even on a monthly basis, because if we have positive and negative numbers the same day, we can't add up that numbers because we are doing something that it's not correct. If at 8 a.m. I have a positive number, and if at noon I have a negative number, it doesn't mean that those numbers are canceled and we don't have any energy. No, I consume energy for heating and consume energy for cooling. So I have to find a way to convey the idea that every single day or every single hour, I can need either heating or cooling. In January, it's pretty straightforward because it's cooling the whole day. But in March, May, June, it might be different. I might need heating and cooling. And that means that I'm spending energy on heating and I'm spending energy on cooling. It's not that I have 500 and then negative 500, the result is zero. No, it's 500 for heating, 500 for cooling. The result is 1,000. So how can I do that? So I need a formula that takes that into account. So first, I'm going to analyze the first month, January. So so once we are done with all these elements, the windows, whatever, I'm going to type here January. And this is going to be January heating. And January cooling. I don't think we will need cooling in January, but just in case. So what's the value of January heating? And here we have the walls. Then we will have the roof. And I'm going to add up all the energy that we need through the walls. Okay, so I'm not going to do northern walls, southern, whatever. I'm going to add up all the energy that I need through the walls. Okay, so the easy way, this is what we did on Wednesday. it's not enough. It will work in January, but in other months, it won't work. But we're going to do it easily. So if I insert function and it's the sum, okay? What's the range? I want to add up every single value that we have in the walls, north, south, east, and west, from January the 1st at midnight until January the 31st, the 31st, sorry. January the 31st at midnight too. So if I do this and I click OK, I have this value from the walls. It's 1,948,700, and so those numbers are so big that they are difficult to understand, okay? Because they are it doesn't make any sense having decimal places if we have the units are millions. The decimal place doesn't make any sense, so that's why I have selected no decimal places. Okay, so January heating, it's this. So we have add up all the values that I have from the north, south, east, and west from January the 1st until January the 31st. Okay. And it goes from, if we look at the number, we have from H2 to the column K and the row 745. Okay, so look at this number. What I have here equals sum H2 K 745. So this is what I have in January. It goes from cell number 2, from row 2 to row 745. If I'm adding up all the columns that have to do with the walls, the first column is H, the last column is K. Okay, so if I type this, I know that I'm analyzing all the heating loads that I have in January. What if I want to do the same for February? It's not going to be from H2 to K 745. I know that we have to start on H, on the column H, because it starts here. So this is February. Okay, so this is month number 2, day number 1, hour 0. So this is February the 1st at midnight. So I have to start in this column. And then I can go to the end of February. If we have number 3, that's March. Okay, so this is February here. This is February the 28th. Oh, joder. Okay, but I'm going to write down the, okay, I'll do it again. I start on age 746. And I want to go to K, and what's the number of the row? I start here, and I go until the end of February. This is K 1417. Okay. I'm going to do this. I'm going to type, instead of selecting the cells, I'm going to type the numbers here on this Excel file. Okay, so here we have January heating and January cooling. I assume that we don't have any January cooling. And now this is February heating. And we're going to have February cooling. So what's February heating? It's the sun. I just copy this. I paste it here. But now it's not from H2, it's from H 746 to K 1417. There you go. Okay. So if I click this, all these cells are highlighted and they go up to February the 28th. What about March? March will start at H 1418. And what's the end of March? I'm going to write it down again. (1418), and I go to K. What's that cell? Let's find out. It's the end of March. It's 2161. Okay, if I just copy and paste it here in March, heating. If I paste it here, I have a value. If I double click here, I have selected all the values that I have in March until this one. Okay, because clicking a column and dragging, it works when we have a limited amount of cells, but when we have hundreds of cells, we can make mistakes very easily. So I think typing things, it's more accurate, and then we always can check if what we are doing is the right thing. Okay, what will be the same value but for roofs? The only thing that changes, it's the column. We have column L. But the values of the rows are the same. So what's the January for the roof? If I copy this one, here. So the thermal loads of January for the roof will be the sum from L, sorry. L 2 to L 745. There you go. I click this, and this is yeah. So we go up to January the 31st. And then what about the February heating? Well, the same. I'm going to copy this one. I'm going to paste it here. And that will be J 746 until J, no, L, L, not J, I don't know why. L. And if I double click here, we will have the value of the roofs in February. In March, the same thing. I copy all this, paste, and it goes from L to L. Yep. Unfortunately, this is not enough, okay? Because we are just adding up all the numbers, and we have been adding numbers in January, February, and March. It's very unlikely that we have cooling loads in either in January, February, or March. But as of April, we might have days in which we need cooling, and which in other days we might need heating. So that's why we are dealing with January heating and January cooling. Okay, I'm going to do something now, and if everything goes well, the January cooling is going to be 0. But at least I will get the right formula. And what's the right formula? It's not just sum. Okay, but now the good thing is that I know the range of cells. I know that I have to go from H2 to K745 for January, H746 to K1417 in February, so on and so forth. But the formula is going to be different. So what's the formula? I'm going to type equals sum if. Okay, so what is this? Sum if means that I have a criteria. So I add up things in cooling, in heating, sorry, if the number is positive, and I add up cells in heating, I'll start over. I will add up things for heating if the number is positive. I will add up things in cooling if the number is negative. So that's if. So that I need a condition. If the number is positive, then I add it up. If the number is negative, I will add it up in a different cell. So let's try to understand this sum if. Here we have a hint. We have a range, we have criteria, and then we have the sum range. Okay, so what's the range? The range is this. It's H2 to K775. So the range is H2 to K745. Then I have to type comma. And then what about the criteria? I need okay, so I need to type this for the criteria. I need to type this symbol, quote. What is the criteria? It's greater than 0. A number is positive if it's greater than 0. So I type this 0, quote marks again. And I need another sum range. Well, the sum range is the same. It's H2 to K745. So if I do that, I have exactly the same number that I had before. Why? Because all the numbers are positive. What about the January cooling? The January cooling, I'm going to copy exactly the same formula, and I'm going to type it here. The only thing that changes is the condition. It's cooling, it's the number is lower than 0. So I have to type here lower than, but the range is going to be the same. And then this is 0 because we don't have any cooling loads in January. But we will keep doing that in summer, and in summer we are going to have heating loads and we are going to have cooling loads, because there are days or hours in which we need either heating or cooling. Okay, so I assume that if I type these formulas in February or March, we're going to have zero. Let's do that in February. I'm going to copy this. I'm going to type it in February cooling. Paste it. And I have to change the range. What's the range in February? It's H746 to K this. So I copy. Paste, the criteria is the same, lower than zero, but the range changes. So we don't have any cooling loads in February. What about in March? In March cooling, I'm going to copy the same. No. I'm going to copy the same formula, the sum if. But the range is different in March. In the range in March is this. And we don't have any cooling load in March. Makes sense. So we will have to keep doing this in April. There will be April heating and April cooling. May. May heating and May cooling. June. So let me see June, because I want a month in which I have both heating and cooling to check if that works. Okay, so in June, okay, in June it works because as you can see, we are in June, month number 6. And there are moments in which we have positive numbers, that means heating. We have negative numbers, that means cooling. So I can add up, I can use the sum function. I have to use the sum if function. So what's the range in June? In June, I have to start on H3626. That's going to be June. And the range is 3626. And the end of June is June the 30th. It's 4345. So that will be K 4345. Okay, so now I go back to this, and I'm going to calculate the June heating loads. So heating is this formula, but I have to change the range. The range is this. And that. Okay, so we have a positive value for the for the June heating, and I want a negative value for the June cooling. So if I change the criteria to lower than, will it work? Will it have here a negative value? I do. Right. Okay, what does it mean? It means that I have to spend money. I have to spend the energy in this building. Most of the, yeah, I have like 166, 557 BTUs for heating and only 74,000 for cooling. So let's analyze these figures. What's the January heating energy that I need? Almost 2 million. What's the June heating load? 160,000. Doesn't make sense. Of course, it makes sense because the value in January it's 10 times, more than 10 times as high as the value that we have in June. In June, we need cooling, but even in June, the temperature is still mild, and the cooling loads are not a lot, okay? Because we don't have severe summers in this area of the world. Can we do the same in July? Probably in July, the cooling loads will be higher than the heating loads. Let's try to find out. July heating and July cooling. The first thing, we need the range. So what's the range of values in July? In July, I have to go to month number 7. So this is 4346. So in July, this is 4346. And the last day of July will be 5089. So now I have to go back to the Excel file, the beginning of the Excel file, and here we have the formulas. I can copy the formula, and I just need to change the range. So the range is this one, sorry. Okay, the heating loads in July are lower than the heating loads in June. That makes sense. And the cooling loads in July will be higher than the heating loads. I changed the criteria. And there you go. Okay, so that makes sense. In July, we have more cooling loads than heating loads. In January, we don't have any cooling loads, we only have heating loads, and so on and so forth. But this is the energy that I need to use. So it's not that, oh, I have negative 100,000 and positive 78,000. So the result is negative 30. No, it's not that. It's that I need 78 for heating and I need 113 for cooling. Okay, so I'm spending energy, but I'm spending some energy in heating, and I'm spending other days, I'm spending energy on cooling. Or over the same day, in the morning, I need heating, and in the afternoon, I need cooling, or the other way around. But when we are dealing with so much data, that's important. I know probably it's too much for a Monday at 8 a.m., but believe me, we are doing some. This is not just calculating thermal loads. It's understanding what's going on with the building. And the things that are going on with buildings are complicated because it depends. Yeah, so we have walls, we have thermal insulation. We understand this. We have inflation and the solar gain, a lot of things. But depending on the outdoor temperature, I might need heating or cooling. And it's not, oh, January, I need heating. July, I need cooling. Nope. In this area of the world, in January, you always need heating. In July, you always need cool. You can, sometimes you need heating, sometimes you need cooling. In Florida, I assume that it would be the other way around. So in summer, you always need cooling, and in January, some days you will need heating, some days you will need cooling. Okay, so depending on where we are, we have to analyze it, but we can only analyze this if we have hourly data. And we have to deal with it. So when you are using professional building simulation tools, you just introduce the data. It's overwhelming. It's not just the thermal insulation, the thickness, the thermal conductivity. No, there are thousands of things that you can introduce. Then you click run simulation. It takes a couple of hours. And after 2 hours, you have values, graphics. And sometimes we don't understand what's going on. I think doing this, you get to understand what goes on here and what goes on. A lot of things that in July, we might need heating and cooling, not at the same time, but probably at different times on the same day. That's the. So that will be our. So we need to create a table in which we have January heating, January cooling, up to December heating and cooling. What about the roofs? If we want to understand the heating loads through the roof, I can copy the same formula, and I only need to change the range. Okay, and what is the range? It's L because the roof, it's the column L. So if I type here L, 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 L. So that's the heating load that I need in June through the roof. If I copy this, paste it here, and I change the criteria, I will have the cooling loads that I need in June because of the roof. What about July? I paste this formula. If I change the range to L, and now if I copy and paste the formula and I change the criteria. I have the cooling loads in July. Okay, so what's the goal this week? We have to finalize this table. We have to finalize this table from January up to December. And we have to include here different columns, walls, roofs, basement, ventilation, windows. And if we are done with this by the end of this week, next week, we're going to start finalizing something that it's it's related to your designs. Because now we have a lot of what if we change the thermal insulation? What if we place this 20? All the numbers change immediately. Okay, so just by changing one parameter in one of these tabs, everything changes there. Doing this by hand, it's impossible because there are so many things. There are so many things to calculate